In this problem, we have a motor here at A that has a radius, an inner wheel radius here of 4 inches. It initially starts with an angular velocity of 0 radians per second, and it has a constant angular acceleration of 5 radians per second squared. That's connected to pulleys B and C with a belt. C and D are connected together as one piece, and D is connected to pulley E with another belt. E and F are connected to each other, and F is winding up this rope to this block G, which is sitting on the ground. So B has a radius of 4 inches. The inner wheel on CD, C, has a radius of 3 inches. D has a radius of 10 inches. E has a radius of 3 inches. F has a radius of 12 inches. And the block starts on the ground, so its initial position is 0. We want to find the velocity of the block G and the position of the block G at a time of 6 seconds. To start this problem, we know that we've got a constant acceleration going on, a constant angular acceleration at A, which means that throughout this whole process, since they're all connected, we have a constant acceleration problem. So in order to start this problem, we're going to look at what's going on here at G. So if we want to know what the position is of G at a time of 6 seconds, we're going to use our constant acceleration equations to find our final position at G is equal to our initial position plus initial velocity times change in time plus 1/2 AT squared. We have a time of 6 seconds, so this seems like the appropriate equation. Our initial position is 0. Our initial velocity, since our initial angular velocity at A is 0, that means the whole thing starts from rest. So my initial velocity is also 0. So my final position is going to be equal to 1/2 my tangential acceleration times the time squared. I know the time, I just need to find what my acceleration is at G. So now I'll need to work through this process of moving from one pulley to another. Because this is connected by a belt, the tangential acceleration at A will be the same tangential acceleration at C. So starting at A, the acceleration at A is equal to the angular acceleration of A times the radius of A. But because the acceleration of A is also equal to the tangential acceleration of C, then we know that it's equal to alpha C RC. So alpha C is equal to alpha A RA divided by RC. However, alpha C, the angular acceleration of C, is the same as the angular acceleration of D because they're connected. So this is the same thing as angular acceleration of D. Now the tangential acceleration at D is equal to angular acceleration of D times the radius of D. We know that the angular acceleration of D is equal to the angular acceleration of A times the radius of A divided by the radius of C. So substituting that in, our tangential acceleration at D is equal to alpha A RA over RC times RD. The tangential acceleration at D is also equal to the tangential acceleration at E, which is equal to the angular acceleration of E times the radius of E. So the angular acceleration of E is equal to angular acceleration of A, radius of A, over radius of C times the radius of D divided by the radius of E. This is also the same thing as the angular acceleration of F, since E and F are connected. The tangential acceleration of F is equal to alpha F times the radius of F, which is equal to angular acceleration of A, radius of A, radius of D divided by radius of C, radius of E, times the radius of F. But the tangential acceleration of F is also equal to the acceleration of G, since they're connected by that rope. Now we have an equation for the acceleration of G, and we can plug in what we know to find out what that acceleration is. So the acceleration of G is equal to the angular acceleration of A, which is 5 radians per second squared, times the radius of A, which is 4 inches, times the radius of D, which is 10 inches, times the radius of F, which is 12 inches, divided by the radius of C, which is 3 inches, times the radius of E, which is also 3 inches. This gives us 266.7 inches per second squared. However, we probably want this in feet per second squared. So we've got 266.7 inches per second squared, and 1 foot is 12 inches. So if we divide 266.7 by 12, we get 22.22 feet per second squared. So that is our acceleration of g. This is the acceleration of g in inches per second squared. This is in feet per second squared. Now we're going to take this and plug it into our equation here. So this is equal to 1/2 22.22 feet per second squared times 6 seconds squared. So our final position of g is equal to 1/2 22.22 feet per second squared times 6 seconds all squared, which equals 400 feet. So after 6 seconds, the block has raised 400 feet. That's a pretty fast pulley system, but that is the answer. But we still need to know what the velocity is of g at the time of 6 seconds. Using our constant acceleration equations, final velocity is equal to initial velocity plus acceleration times the time, which in this case, our initial velocity is 0. So our final velocity is our acceleration times the time, which is 22.22 feet per second squared times 6 seconds, which will give us 133.3 feet per second. Now we have both our position and our velocity at a time of 6 seconds. And that concludes the problem.